Good evening and welcome everybody. It's Obi-Wan Piz. We're in Simplex Pachinko and we are doing some math tonight. So, I hope everybody's having a good time. Hey Laz, how's it going? And shift this window over here. And that's everything. Okay. So I hope everybody's had a good weekend. I did some streams, but yeah, I spent most of my weekend thinking very long and hard about Slay the Princess. And Carolus, to your credit here, yep, it was at least partially your doing. Watched 2 streamers and now I'm on a third one to like really solidify it. I think number 2 really kind of did solidify it, and she's YouTube exclusive. That's her YouTube handle. I recommend her playthroughs because they're like thorough and scientific almost. I asked on her Outer Wilds video, like what was her background that she was so like scientifically minded in figuring this stuff out. But I don't know that I checked for an answer. I was gonna say I don't know that I got an answer, but that's not true. I didn't look. Slept too much, yeah. PSAT or PSET? If it is PSET, I don't know what that is. This past week, we got probably 2 weeks ago, I finally got all of our rolls of film finally taken out of our house and developed at this local center that we got. There's nothing really that's like super worthwhile in there, especially anymore. It's been over 10 years since we actually since these were taken. So the film itself was kind of we had our moving truck that was going from one house to another that was stacked full that I just thought was amusing. I was taking it out to the truck to be packed, and then I just was like, so I took a picture of the truck. Yes, it is slideshow day. Some pictures of, I think, Scotland, but like the development got completely screwed, because I think some of the stuff on like the outer edges ended up getting exposed due to radiation. So whether that be X-ray going through the X-ray scanner, or be it just ambient radiation due to either radon or number of other things, like one of the rolls got completely ruined. Oh yeah, here we go. That's awesome. And the other one's fine, but like there's a lot of overexposed stuff, and I was doing a lot of experimentation on this particular roll, I think, with trying to set different light levels and things like that. So there's a lot of just completely unusable stuff. It's great. And like I said last week, you know, my grandfather passed. Again, it was expected. My mom has since been like, yeah, don't worry about coming back to the States, you worry about your family. And I'm like, mm. I mean... So she's going to let me know if they need anything, but they're not having a memorial ceremony until, I think it was spring. So they'll let us know then. And there's a good chance that we'll be able to head back to the States for that one. And as much as I hate to say it, there's a possibility that we're going to lose at least 1 or 2 more people before then. So that is also I mean, it's not good, but it at least, you know, it would give the family more time to be able to prepare and possibly, you know, like I said, we're possibly going to lose a couple more people over the winter, and having them all kind of at once, like celebrate everybody at once, I think family-wise might end up being slightly better-ish, if it could even be better. I'm just talking now. So, I hope everybody had a good weekend. And maybe let's take a look at Fourier series. This was another section of differential equations that we were going to talk about a little bit. And we got to do a little bit of it when we were just chatting in our differential equations class. But we never went over like the broader scope of it. I will say that I'm not super great at this. It's been a number of years since I did it, and if anybody has any particular questions that they would like answered, please interrupt me, because otherwise I'm just going to keep going on about this. Alright, so we talked about, last time we had mentioned this in differential equations class, that there is the cosine Fourier series, which says that we're going to take the integral from 0 to pi of f of x dx, and that is going to be equal to a sub 0 over 2 times the integral 0 to pi dx plus the sum as n, I hate n doing that, k goes from 1 to infinity. You could also have that k goes from 1 to n, limited as n goes to infinity, of a sub n times the integral from 0 to pi of cosine of n. Ah, is that why they did it? Okay, k pi. dx. Okay, where f of x is equal to, this is a sub 0 over 2 plus summation, k goes from 1 to infinity, of a sub k. Ah, I missed that one too. See? sub k times the cosine of k pi. Alright, and as long as x is represented somewhere, or as long as x is defined for all values between 0 and pi, we can do this cosine Fourier series, which then represents, like, basically any function that we feel like. We did talk about the idea of representation, where it doesn't have to be a 100% perfect match like term for term for literally everything, but when you sum up an infinite number of cosines with an infinite number of frequencies over this kind of over this range of values, then it can end up, much like a Taylor series, it can end up mimicking, essentially, which then converges to the exact values of any function that you would like, any continuous function you would like. What was C sub p? I didn't actually look at that. Yeah, piecewise. Okay, piecewise continuous functions defined on the interval as x goes from a to b is a function space. So. So in this case, this particular f belongs to the function space C sub p of 0 pi. So again, piecewise continuous within everything from 0 to pi over, yeah, all those real values. Right, because z is not going to be complex valued or anything like that. Yeah, probably continuity piecewise. Okay, so analogous to three-dimensional space, linear combinations of vectors are all well-defined vectors within that space. Okay. So when we do that one, it's going to mean that the integral from 0 to pi of f of x dx is going to also be equal to a sub 0 over 2 multiplied by x taken from 0 to pi plus a spooky music. Ghost Waltz. right, times the sum as k goes from 1 to infinity of a sub k being a constant times, here we get we went from a cosine, now integrate it to a sine of k of x. And for all of these values, depending on what the k value is, we would need that particular k value in the dx term in order to make our u substitution work. So this ends up being divided by k for all possible values, and then evaluated from 0 to pi. Now this is an infinite sum, which means that all of those terms are going to end up being 0. Right, as long as k is an integer. Right, and x will be not always an integer, so therefore when k is... no, sorry. I thought that was supposed to do something else. No, that's fine. Ah, right, okay. No, I'm still going backwards on this. Yeah, right. You know what, let's not even when this. Let's just straight up. Right, we end up taking the... That's okay. Sine of k times pi over k. And each of these individual terms could be matched up with their counterparts. So here, it's going to be minus the sine of k times 0 over k. Right, so all of these terms are just going to be 0 because it's the sine of 0. And all of these terms are going to be 0 because k is an integer. And all whole integer times pi, when we take the sine of that number, ends up being 0 as well. So this ends up with a sub 0 over 2 times pi minus 0. Again, same deal. We subtract, you can do it in parentheses if you really want, but it doesn't much matter. Is going to be equal to the integral from 0 to pi of f of x dx. Right, then try to isolate a sub 0, and that's going to get us integral. That's fine. Integral of f of x dx from 0 to pi times 2 over pi. Right, when our constants get in there. Ahoy! Rip Eagle. How's it going? My name is Obi-Wan Pez. This is N Simplex Pachinko. We do mathy stuff on Tuesdays. Yes. I'm trying to relearn a little bit of Fourier series out of my book, which is 20 plus years old at this point. Brown and Churchill, Fourier series and boundary value problems. If you have any particular questions or things you'd like to talk about, anything like that, let me know and we can discuss. I'm mostly only really good up until bachelor's sophomore year, which is where I was teaching. I was teaching at a community college in Maryland in the United States, and our family has since moved to the UK, where I'm now essentially full-time person, house person. So, speaking of which, I have to go grocery shopping tomorrow. Woohoo! Analog electronics and signals. Yep. I have a bunch of friends who are in signals processing. Those were sort of like the parallel classes to what I was taking in masters, and that was 15 years ago. So we're trying to, again, I'm just trying to learn some of the old stuff all over again. Nice to meet you too. Otherwise, we're just vibing. Okay, so let's see. Yeah, we just had a, finished up a couple weeks ago, a differential equations class that I was teaching, which was the same one as all of the student at Masters. Yep. It was the same undergrad ODE class that I was teaching at my community college, and the same one that I took, goodness, essentially 3 times. Asterisk. I took it once in undergrad as my sophomore year ODE class. I took it once as my master's level. So because I didn't do so well at this other... Alright, I was at the University of New Hampshire. I had mono. And my first semester in this special class, so we had this... we had a special program. Alright, this is going to take a minute. We had a special program where a bunch of us, all of the physics majors and all of the math majors, and I think there were a few other engineers, other people like that, were invited to take a studio calculus and physics class, which taught calc and physics together at the same time and doing all that stuff. Renewable energy and materials physics. Awesome. I had one of my friends was into materials physics. Come to think of it, I don't know where he is these days. But yeah, he was telling me all sorts of stuff about, man, you be glad that you left being a physics major. I was like, I mean, it can't be that bad. He was like, no, it's so much work. So I was originally going to be a physics major with the intent of going into astrophysics with the intent of doing some black hole physics. I'm just looking at all the stuff I missed out on. Anyway, so I took studio calc and physics with a bunch of my other fellow physics majors. We did all right. It was kind of interesting. I really enjoyed a bunch of it. End of the year came and we did we were doing a group project, and there was one guy who was like, nah, I got it, don't worry. So the idea was to his idea was to build a system where you could input music into it, and it would output the fast Fourier transform and then translate that using a special encoding algorithm into letters, and so you could encode and decode messages using this particular system. Kind of cool, interesting. It wasn't secure or anything. It was just kind of a proof of concept, that the fact that it worked at all. And so the rest of the like 4 of us who were all physics majors kind of sat around and did the presentation part of the project. And while we were waiting for him to code it up so that we could get more results, so that we could do like, you know, the last half of it or whatever, one of the other guys was like, you know, we're all just gonna be teachers, right? Everybody was like, oh, it's sad because it's true. And I was sitting there and I'm like, you know, passing the information on to the next generation, doing my part to be the this, that, and the other thing. And I was like, yeah, you know what? I think that's it. So that's the moment that I switched and ended up doing math education rather than physics. So I was also staring down at the next physics class in our sophomore year was going to be thermodynamics, which had a pass rate of 39%. And I was like, I don't know if that's really my kind of... I don't know if that's my kind of climate. So I am much more of an armchair physicist. I do have... Oh, I left those upstairs, didn't I? Boo. I do have a brief history of time. I do have several other cool books that I enjoy. Neil deGrasse Tyson's Astrophysics for People in a Hurry, little book of exoplanets, which my mom found and gave me before we left for England. Yep. How the Universe Got Its Spots by Jenna Levin, who is also a good friend of Neil deGrasse Tyson, and Brian Greene's The Elegant Universe. So there's, yeah, those are, you know, that's like the stuff I keep within easy reach. I also have Dr. Becky Smethurst's book. I don't know where it went, come to think of it. I think my daughter took it. Oh, I'm actually watching his series Sensation, the one that's on BBC iPlayer. So I watched 2 of them this morning and had a good nap somewhere in there. I need to work on that one. Yeah, no, that's true. Brian Cox says that a lot. I was referring to the new one specifically that everybody's pushing, like, right now. In fact, if you open BBC iPlayer, it's on the homepage. And, Rip, I don't think he was specifically talking about you, so... yeah, it's... So, Sensation's been doing a lot of work at tutoring. Yeah, I still like the original Cosmos. I think probably a little bit better, just because that's my bias of liking Carl Sagan talking like this. But yeah, Neil deGrasse Tyson. I listen to his Star Talk podcast like every week. Yeah. So we had actually watched a couple episodes. I'm not sure about the whole thing, but a couple episodes at least of Cosmos after I became interested in astronomy and physics as like a 10-year-old. And then our high school middle school, high school. I think it was high school. Um, oh, actually, he just passed away too. My this is gonna happen more and more in my life. My history teacher in ninth grade, and he was also my 12th grade psychology and psychology, not sociology. My 12th grade psychology teacher um, used to stand in front of the board, and he had this really thick New York accent, and he'd always talk about the cathedrals with their big windows, and I always talk about the people. It was a little bit slightly New Hampshire as well, but mostly New York. With their eyes looking up the ceiling, and the cathedral with their flying buttresses and all this other stuff. And he would draw these things all over the board, and we'd just be like, okay. I don't understand exactly what exactly is going on here. But sure, we're copying all this down because we're ninth graders and we're very obedient, and we're going to listen, and we're going to copy everything you write. I still have it in one of my notebooks. I gotta find it. It's around somewhere, but yeah. But yeah, his name was Mr. Smith, and we would always talk about the Smittyisms that he would put on the board, and the Smittyisms that were his key phrases that he would use all the time. But in ninth grade, he also made us watch Jacob Bronowski's The Ascent of Man, which is an excellent series, but it is very old. I mean, it was made in mid to late 70s, and it was showing its age before I was born. Yeah, it was really old. And the guy himself, Jacob Bronowski, is 1950s type professor of I don't remember exactly where he was from. I think it was probably Oxford, but so yeah, Sensation. I've had the same issue with the kids at my community college who wanted to go to the University of Maryland, which is kind of their next step, right? They get done with community college with us, and then they want to go on to University of Maryland. And so many of them, it was just okay, look, you need to use all the resources you have, including the Writing Center, which is in our building right over there. And they just, half of them wouldn't listen to us. The other half of them actually understood, oh, yes, maybe that's a good idea. I probably do need some extra help with this. Hey, can you look over my resume? All right. Also, you could go to the Writing Center for this. Yeah, so Mr. Smith had us watch Jacob Bronowski's The Ascent of Man. He had us watch an episode of Cosmos, specifically that had to do with science history, that sort of stuff. And he had us watch he had us watch Schindler's List. Oh, that was rough. Every single person in that room was crying. We're just we're ninth graders. We're not supposed to be crying in front of each other, but it was just tears everywhere. And I mean, you're supposed to cry at that movie, but Yeah. Yep. um, I teach. I mean, I taught just pre-calc, but I was also teaching as part of the honors group. What was it? The honors scholars. What were we doing? It's only been like 5 years. I mean, I should know the abbreviation and stuff for it, but yep. Oh. Phone. Cow. Yes. Jim Henson was a genius. Okay, so while we're looking at this, and Jim Henson was born around the same time I was. I knew that one offhand. Alright, so based on this thing, okay. So now while we're looking at this, we could say that our f of x is going to be equal to, here we can use the a sub 0 that we just found. So 2 over pi integral 0 to pi of f of x dx, which now this thing is implicitly defined on itself. So, a little awkward. However, is that not what we did? Maybe not. The seatbelts. Is that an AI? Oh. That's fair. No. So I'm not doing this right for writing it out the way I want it. Okay, so f of x is equal to a sub 0 over 2 plus we had up top k goes from 1 to infinity of a sub k cosine of kx. Okay. Then we can rewrite f of x is going to be equal to a sub 0 over 2 plus summation as right, back up through the alphabet. A sub j cosine of j x and then we're going to use cosine of kx, where k is any fixed integer, and make this f of x times cosine of, yep, no, that's right, kx, equaling a sub 0 over 2 cosine of kx plus summation j goes from 1 to infinity of a sub j times cosine kx cosine jx. Right, because that's multiplying in through all this stuff. Okay, and then integrate all terms. All right, the summation and the a sub j are all constants with respect to x. So we can have that integral be on the inside of the summation, or we can have the integral be on the outside of the summation. It doesn't change anything. All right, when we do that, we've got our integral of f of x times cosine of kx dx, which is that anywhere above? Question. No. Okay, good. It's new. Okay, is equal to a sub 0 over 2 times the integral of the cosine of kx dx, which right, we found that up here. The integral of the integral of the cosine of kx dx is equal to 0 because we had that in both of those pieces there. So this brick here, it's going to end up being 0. Again, integrated over finite limits, 0 to pi. Plus sum j goes from 1 to infinity, a sub j times now the integral from 0 to pi of both cosine of kx times cosine of jx dx. Alright, now, in this thing, when j equals k, then that's going to be a sum of cosine squared. Hang on. Oh, yeah, okay. We're going to end up with pi over 2, which we can do in just a sec, because, again, that's going to be the integral from 0 to pi of cosine squared of any particular kx dx. It's going to be 1 minus bump cosine squared down. It's going to be 1 minus cosine of 2kx over 2. I think, right? Sine 2 theta minus 1. Square theta. Hang on. No, that's not right. Hang on. Been a while since I've done these. Getting rusty. Oh no. 2 cosine squared theta minus 1. Okay, so cosine squared theta is going to be equal to 1 plus cosine 2 theta all divided by 2. Okay, plus. We're getting there. Alright, 0 to pi. Alright, so 1/2 x plus now, this is where we end up with the sine bit. So, sine 2kx over 2k evaluated from 0 to pi. Evaluated from 0 to pi, again, all of that. It's going to end up being 0 no matter what k is. No matter how fast this thing's going. Right? That whole thing is, that sine value is just going to be 0. So we end up with exclusively pi over 2 minus 0. That's really cool. I like that. Right? This is frequency invariant. That's really cool. Okay, so when j is not equal to k, right, that's what happens, what's going to happen here. Oh, we could do product to sum. I hate these, but you know what? It works. So I don't know what the product to sum to product formulas are because I never learned them and I hated teaching them, and I told my students, you will never ever ever have to learn this as long as I am the coordinator. I just pointed them at it and said, okay, use your sum formulas in order to figure this stuff out, but you don't have to worry about it from me. So when we did this, this was cosine of like k plus j. Yeah. It's going to be equal to cosine times x. Right, cosine kx, cosine jx. Minus sine kx, sine jx. Okay. Cool. Now we're just kind of kicking the can at the moment, but okay, so when we take the integral of that part, that's at least going to just end up knocking it out and becoming 0 again. This stuff... I'm going to hold off before we... look it up. But... if anybody knows it offhand without looking up, right? How do we get rid of this bit in our product sum to product formula? Now I will say I probably should have actually looked this stuff up and like played around with it some, even though I wasn't teaching with it. I probably would have thrown it in class a couple of times and just been like, ah, look at this. How cool is it? And everybody would want to institutionalize me. Okay, well, calculus-wise, right? If we do this, 0 to pi, right, dx, this is still going to get knocked out to 0 for the same reason that all the rest of these do. K plus j is closed under addition for integers, and therefore we still get a cosine of an integer times x, which we are integrating over 0 to pi, which is still going to get us a sine of that same thing, which is still going to get us 0 when evaluated from 0 to pi. Okay, then the next part is that one. So what do we do with that one? I'm gonna resign to integration by parts, I think. I feel like there should be a pre-calculus way for us to figure this out and make it a little bit nicer, but for right now I'm willing to just go with a calculus solution. We'll look up the pre-calc one later, I think. So integration of these two things, sine kx, sine jx, right? One of them's got to be the derivative, one of them's got to be integrated in order to get back to the next one. So we'll just go uv, udv without loss of generality, because it could be either one, doesn't matter. It's going to be equal to uv, which is going to be sine kx times v. We take the integral of that sine of jx. We end up with a negative cosine of jx over j minus integral of v du, which is going to be that same negative cosine jx over j, times du is going to be k cosine kx dx. Okay, we take the pluses there, and then we have to do the exact same thing. So the j needs to be our dv, and the cosine kx needs to be our u for the next term. So that one is going to end up being, this part is going to end up being uv. We could take the constants out front. So k over j, get rid of those. Have it not be part of the integral for now. uv is going to be the cosine of kx times v is a cosine, becomes a sine, jx over j. Move over. Minus integral v du is going to be same kind of deal. Sine jx over j times k, this is going to be a negative k cosine kx dx. Oh, sorry, that's a cosine, so this one needs to be sine. Whew. Right, because we had a cosine, we take the integral. Nope, take the derivative, it becomes a negative sign. Okay, so that's here, which means that we get a plus k over j here. Right, that's gonna be fun. Integral sine kx sine jx dx is going to be multiplied by 1 minus k squared j squared. K squared over j squared. Right, from the portions on the other side, we're going to subtract them over, and that ends up with that. Alright, we're going to start an ad break. Get something to drink, get something to eat, stretch your legs, walk around, do some exercise, and we'll be back in 3 minutes. Thank you very much for sticking around. We'll be right back, everybody. This is Obi-Wan Pez for and Simplex Pachenko. Hanging in there. So, as is typically the case, if nobody else redeems it by this point, I usually redeem doing some martial arts. In this case, this was, what's that one called? Shinte, which is a black belt form. It's usually the first black belt form that you learn as part of your first degree brown belt. So, that's fun. And the fact that I remember it without major error, I think, it's pretty good. It's been 6 months since I've really been in that karate class, so it's good to do it. I also did, let's see, last week we did some eskrima. So we have our trusty eskrima sticks that we use to hit things with. Sort of. I also need to get actual eskrima sticks. Right now I've got these polycarbonate ones, which completely destroy everybody else's. I really shouldn't do that. Alright. So, compared to what we had last time, right? This was going to be that. It's going to be equal to... Got a negative sine kx cosine jx over j. K plus k over j squared cosine kx times sine jx. Means that the integral of sine kx sine jx dx is going to equal to we're going to multiply by j squared over j squared on the next turn, because I know where this is headed. This is a negative 1 over j sine of kx cosine of jx plus k over j squared cosine kx sine jx. Okay, and then all divided by 1 minus k squared over j squared. Okay. So when this j squared all multiplies in, it's going to clear this bit out. It's going to make this a j squared, and it's going to clear that out. j squared over here. We're going to get 1 up top and none on the right one. I feel like that is a... I feel like that's a product rule. And I'm going to flip those so that this is k cosine kx sine jx minus j sine kx cosine jx. All divided by j squared minus k squared. It is so close to being a product rule, but it isn't. Because those are both sines turning to cosines, which means that the signs stay the same. So there should be a plus in between them, if it were a product rule. So close. Suppose we could change j to become like negative m, and then have it go again, but either way. So that technically is what would replace the other crap up there. I don't like it. Right, this one right here. We've actually... No, wait, hang on. Is that what I did? Yeah, when j is not equal to k, what do we get here? Oh. Oh. But if we apply that x is going from 0 to pi, then both of them have a sign in them, which means that both of them end up being 0. Alright, cool. Right, so if we change this from 0 to pi, then we change this also from 0 to pi, x equals. Which means that our sign here and our sign here are both going to be 0. Okay. So whenever j is not equal to k, we end up just getting 0 out of all of this. You know what, let's highlight that really big. So, welcome to Fourier transforms. Not transform. Welcome to Fourier series. So that makes everything like super easy comparatively. Right, we're gonna do this. So therefore, right, the integral from 0 to pi of f of x cosine of kx dx is going to be equal to a sub, nope, that one, right, the sum so the sum of, is that what we got here? That's not what I have here. So let's think about this a little bit. So what I have now is a summation as j goes from 1 to infinity of a sub j times conditional 0 whenever m is not equal to j. No, k. Whenever j is not equal to k, and pi over 2 when j is equal to k. Right? Yeah. K is a singular value which exists on the other side. Okay. So it's a summation of a bunch of zeros, and then the 1 pi over 2 times a sub k, which exists on the other side as well. Integral 0 to pi f of x times the cosine of kx dx. So therefore a sub k is going to be equal to 2 over pi times the integral from 0 to pi of f of x cosine of kx dx. Right. So So looking back, what we had, integral of f of x dx from 0 to pi was going to be equal to a sub 0 over 2 integral of, did I mean to put f in there? No, I did not. Okay. No, because that was, okay, that's a separate thing. Okay, so that's going to be a sub 0, and then all of our a sub k can be represented by this thing that we just found out here. Right? Got an a sub 0 here. Okay, so f of x is going to be equal to a sub 0 over 2, which is this thing, or just 1 over pi times the integral of f of x dx from 0 to pi. This is implicitly defined, which I know is awful, plus summation all of our a sub k's, which is defined below, times our cosine k pi. dx, cosine k of x dx. Cosine of kx dx, right, times cosine k of k pi. That can't be right. Right, that's not supposed to be pi, that's supposed to be x. There's something looked wrong. X being between, not inclusive, 0 and pi. Alright, so x at 0 and pi ends up getting us those integrals which have values of 0. Boy. It was never really meant to do that with. It was just a matter of figuring out some other representation for it. Okay. What they actually want us to look at is now say that. Okay, we can't be certain at this time that the representation is actually valid for any particular f. So we said that there is a correspondence. F of x is corresponding to a sub 0 over 2 plus the sum. K goes from 1 to infinity. A sub k cosine kx. Okay, maybe written more compactly with coefficients that were given as this thing, which actually is, I believe, what I wrote over here. So actually. Okay, so they said that when you rewrite this, it's not going to be implicitly defined, haha, because we could just change the variable to be something else, like s. S is used for the variable of integration in order to distinguish it from the free variable x. Okay, fair enough. F is piecewise continuous, ensures the existence of the integrals. Okay. F is defined on all values from 0 to pi inclusive. Series converges to f of x for all x within that interval. Series also converges to the even periodic extension with period 2 pi of f on the entire x-axis. So it converges to a function capital F of x such that capital F of x is equal to f of x. Also, it is a cosine reflection, so capital F of negative x is equal to f of x, right? It's even. and f of x plus 2 pi is going to be equal to f of x. Okay, so this is a correspondence again. So the series itself, right, is going to be capital F of x, which is equal to that whole series. And then, again, f of negative x is equal to f of x capital. And f of x plus 2 pi is equal to f of x. Sorry, I just had a thought here. Hey, lads. I mean, we are in the spooky month, so. Right. So, have you done Taylor's series? I forget. And or where are you in the mathematical progression? Hey, Bertram. Good to see you all back. Right. Y'all don't need to see the giant mess over there. Keep telling my kids to clean up. I don't do it. I'm like, alright. You're the ones who have to live with this mess. But then I get in here. Nice. That was the class that I took. I was actually in the middle of that story, and I just kind of trailed off into nowhere. So I was telling Rip Evil about that one a bit ago. Right, I was in that class in undergrad for my sophomore year, and I ended up getting a B my first semester and a D my second semester because I had mono during my second semester. So, you know, I didn't do as well as I should have in, like, any class. GPA was awful. So they were like, Johns Hopkins, when I went there, they were like, yeah, so you got a B, then a D, and then you went back and got a C. We're gonna want you to take this. We're gonna want you to take this other class, which, like, you know, make sure that basically engineers and physicists and other people who haven't taken these classes in a long time are able to take, like, master's level math. So we're gonna have you take essentially that integration of multivariate linear algebra and differential equations, and all of it gets crushed into one. Okay, so it wasn't quite a proof class that does that. It was multivariate linear algebra and differential equations. It was called linearity. When I took it for my master's, I got an A. That was the one that was out of the Krasik book. Advanced Engineering Mathematics. Quite thick. Again, this is 3 classes, so this is as thick as our calc book was at the community college, because it was that one was Calc 1, 2, and 3 in one book. This is those 3 classes in one. So it was a pre-master's level, but yes, essentially it's like a master's prep. Is you better make sure that you know how to do it. So it's review. Review class for masters, you know. So yeah, I have to say it was a good class. The guy who did it was a teacher at, and I didn't find this out until later, but he was a teacher at the Naval Academy. And it is, in theory, possible that had I gone into the Navy out of high school, I was, like, shortlisted to the nuclear engineering program. So I probably could have gone nuclear engineering and gone into the Naval Academy and had this guy as one of my math teachers. But I instead chose to stick at the University of New Hampshire. So I stayed with the University of New Hampshire, didn't go into the armed forces, and stayed well away from the armed services after 2001. So yeah, if I was in the Naval Academy and then 9/11 happened, I would have been like, oh, okay. But as it was, the recruiter was far too excited to have me as a recruit, and I was just like sitting in this office as he's pouring through my ASVAB scores, my just regular academic scores, and my nuclear engineering entrance exam scores, and he's just going, oh, I've never seen exam scores this high. And I looked at my mom and I'm like, and she's like, crap. He oversold it. So I took the nuclear engineering merit badge as part of Scouts because our Scoutmaster was working at Seabrook Station, which is a nuclear plant up in Seabrook, New Hampshire. So he was really excited to share with us how nuclear engineering works. And I was like, this is really cool. I love physics. I love like the merging of chemistry and particle physics and, you know, energy creation, like all of this stuff. Just all of it all together. Now, my mom was a school nurse. But she was with me in the room with the recruiter while he was looking through my test scores. And yeah, he was just like, oh, never seen scores this high. And I'm looking at my mom just like, typical, 17-year-old, just complete teenager, like, really? Is that how we're playing this game? But yeah, he far oversold his enthusiasm, and I was just like, I'm not having it. So I was like, yeah, I think I'm gonna go a different route. And he's like, no. I'm not gonna sign the papers. And my mom's like, yeah, well, don't think I blame you too much. But yeah, I mean, right, having your entire college experience paid for, and sure, you've got to go serve in the military for a few years, like, and you get leadership experience that you can't beat, and you get on-the-job training, and you get all this other cool stuff. Like, it was a good deal, and I turned it down. It wasn't for me, but I will say that it is definitely a good deal if you are into that sort of thing. Interesting, right? Because maybe I wouldn't have met my spouse. Had she taken the job that she had, I would have been in Annapolis while she was still in Maryland. And it's possible, not maybe likely, but possible that I could have met her there. Like just a couple of years later. And also, right, if I had done nuclear engineering, been part of a sub-team, been interested in like signals analysis, then I would have met with many of the people from the mathematical side of the intelligence community. And like, she's sort of tangent to that. It's kind of interesting. Like, she and they have a lot of common friends who do stuff, and it's kind of like, ooh. Just the wild things that could have happened, but yeah, complete coincidence. No. No. I have zero research ever done. I mean, I have done like some research, right, in my own little sphere, but I never actually did anything. So I have done nothing that I would think is publish worthy yet. I think that I have a couple of threads that I can pull on and probably get something together. But the other question is, like, who would even want to publish me? Because I'm nobody, and what I did is not, like, earth-shattering. So, no. So, none of my degrees had a thesis requirement, which is also, like, kind of interesting in its own right. Some people would have said, like, oh, you know, your master's really should have had that. Well, okay, sure. Like, it would have been nice had I done some thesis work for my master's, sure. But we were busy. It was a part of, like, the engineering program for professionals at Hopkins. Takes a lot of the people who do, like, the applied math stuff at Johns Hopkins Applied Physics Lab, which includes space science, which includes robotics, which includes a whole ton of stuff, some of which is classified behind little swipe cards, and some of which is perfectly accessible to anybody. You know, you just basically go there and ask for a tour, and they'd be perfectly happy to walk you around some of the less strict areas. Right, so practically anybody can walk through the unclassified area. You just have to have a tour guide to bring you around. Then you have, like, the defense contractor classified area that, like, nobody goes into unless you have an actual clearance, which I don't have. No. Not that, like, I'm untrustworthy or anything, but it's just like, they wouldn't be interested. It's spooky stuff. I want to see. So the unclassified stuff, they have like posters and things that are all over. You could probably go to their website. It's the Applied Physics Lab, Johns Hopkins University, and there's some really cool stuff that's just like available on their site. So check that out, and they'll tell you what they can tell you. And then there's like, you know, stuff they allude to that's like, you know, oh, we're defense contractors and we've done some stuff in you know, helped out the US government, did stuff with guidance systems, very vaguely, that sort of stuff. So but I've got a lot of random friends who have done math and programming and engineering and physics in some sort of, you know, classified capacity as defense contractors or corporate contractors who work for Defense Department, or yeah. What's the US government hiding? Yeah. So I mean, there's not a lot that you can't just figure out, right? If you have done any amount of like looking into just the unclassified stuff, you could be like, well, if we go a little bit further with this technology, here's where it could end up. And like a lot of that is classified just because they don't want anybody else having it. It's zero grab. God, I wish. Yeah, no, I don't think that there is any zero-point energy manipulators. I don't think that there's any anti-grav systems. I don't think that there's anything like that, because that would be really cool, but nah. All right, what else we got? Yeah, or the capacity to overclock your brain or something like that. That'd be pretty cool, but at the same time, that'd be really serious problem. All right, Sensation. Don't need to abuse the other viewers. Alright, y is equal to capital F of x is obtained by reflecting the graph over the other side. Yep, repeat intervals over and over and over again. Sure, we can do all that stuff. That's all good. Yeah. Oh yeah, there's so many great phrases that I just need to like I need to get in writing. All right, so severe language, I'll allow it only because this is a thing that you will hear very often if you end up in the north of England. Hmm. Really? Fascinating. I was looking up a phrase that I saw. It was at Ripley. We went to one of their festivals, and they had a cafe, and we sat in the, or it's like a restaurant. We went into the restaurant, and it's like a tea shop. Yeah, I think that's mainly their claim to fame. So it's like a tea shop. So they have like a Yorkshire phrase. It's like a miniature, 2-line poem or something like that. And I looked it up. I was like, I don't even know what kind of meanings this is gonna. I gotta look it up again because I can't remember. You probably know what it is. You've probably been saying it since you were, yay big. But nonetheless. Yeah, but I was like, man, this doesn't seem very flattering. Okay, so we got this thing. We said that f of x is... Well, yeah. English also should not be spoken or should not be written with Latin. The Latin, the Greco-Roman alphabet is just terrible for English. I definitely think we should go back to the Greater Futhark, but but also, if you have seen anybody who has played anybody who's played Stray, no, not Stray, Jesus, anybody who's played Tunic, the runic letters that you get in there are absolutely genius. I recommend that everybody play Tunic and actually try to translate the language. I'm serious. Translate the language. It's brilliant. It's amazing. I was like, I vote that we trade out our entire language, like written language, for these runes because they're just so cool. Lack of education. I mean, I would go with more of the, like, the kind of education was certainly different. It was much more farm-raised. And, I mean, that's kind of the same as... If we're honest here, Sensation, that's also the sort of... True. But I mean, that's like the same thing that we got in the States, in like the backwoods areas, right? Like, it's also fair. Like our town had a, now granted, it hadn't been used in 50 years, but our town had a one-room schoolhouse. And we were right next to like a big town. Yeah, so like the my father-in-law was also part of a like very tiny community in North New York. He was around in the, let's see, his schooling was 60s and 70s, I think, mostly. So he was so they had similar conditions. Yeah, okay, not the same, but similar, in that like his town, the only opportunities you had were to get out or to become one of the locals, you know, be a townie. And by townie, I don't mean like, there's a lot that I could mean and couldn't mean there. The so like the townies that I grew up with are people who, generally speaking, have absolute zero ambition to do anything and zero ambition ever to leave. And when I say zero ambition, I mean like not even for holidays. Like a big holiday would be going to Boston. And then saying, ugh, I'm so glad I'm never going to do that again. Nope. Okay. Is that Chav? Or is that something different? Same. Okay, yep. Antisocial lower class youth, yep. Dressed in sportswear, typically, let's see. Yeah, spend all their money on gold chains. Try to be tough guys. Tracksuits, yep. We had a guy who in middle school was already trying to be like basic. I mean, he was dressed that part. You know, tracksuits, gold chains, all that. Was basically trying to get like his own little wing of organized crime going in middle school. I was just like, I don't want to be anywhere friggin' near you. Nope. Nope, nope, nope. I was done with that guy. It's weird that I can't snooze. It's like it's taking yesterday's snoozes. a sub 0 oh, f of x equals x. Let's try to look at it. Yeah, okay. Yeah, they're doing an example in this book. So, right, so if we do example, if f of x is equal to x, then we want capital F of x to be equal to we said a sub 0 is going to be 2 over pi times the integral 0 to pi of f of x dx. Which is x dx, which is going to be equal to 2 over pi times 1/2 x squared evaluated from 0 to pi, which is then going to be, our 2's get knocked out here. Okay, so 1 over pi times pi squared minus 0. Okay. And then a sub n, all other a sub k is what I do. So all other a sub k are equal to the thing we did up above. 2 over pi times the integral Outerget, yeah. No, that was Ripley. Right, so that was f of x dx times cosine of kx dx. Okay, and for this one we need to do integration by parts. We've already kind of done that, but whatever. So that's our, obviously, u. This is going to be dv. U could be cycled down, so we want to do that as a derivative. dv cannot be cycled down, so that drops its priority. And some of you know the friggin' whatever hierarchy acronym that goes with that. I don't really care. All right, so we're going to take a 3-minute break for the ads, and I'm going to go grab a drink, I think, and cycle water or anything else that needs to be done. Stand up, sit down, walk around, do whatever you need to, and we'll be back in 3. Thanks for sticking around. All right, so sensation. I think I understand. I think you might have been thinking that I was talking about Betty's, which I've also been to, but yeah, no, the one I was talking about was in Ripley. I don't remember what the name of it is. It's like this little tiny cafe. I could look it up. But I rode my bike over there on the recommendation of some of the local other American parents. They were like, you really ought to take a ride on this greenway. Runs alongside multiple roads. I don't know. Freaking A6, whatever that is. Hang on. What direction is Ripley? Harrisboro. Wrong direction. Okay. Not Killing Hall. There's Ripley. Yeah, it runs alongside the A61 for a bit, and it dives off into the woods pretty close to the River Nid, and then touches on Attagate, and then goes off to Starbeck and Follyfoot, Aketon, Spofford. Yeah, so it goes off that way. So we, I packed up the kids at one point, and I was like, all right, let's actually like do this ride. We're going to set Ripley as like our ultimate goal. And oh, Ripley Castle Tea Room. Yeah, okay. So they have a... Yeah, the Ripley Castle Tea Room has like a... Ah, there it is. I can't make it out. You know what? I think that's the other phrase. I didn't know what this one was. But, yeah, up on their rafter, they have like a classic Yorkshireman prayer or something like that. Might even be in my photos somewhere. Like, if it is, it's going to be really lost in there. But I sat in the corner with my kids, had a coffee, had a drink, and... Oh, yeah, that's it. See-ol, ear-ol, say not. A-ol, sup-ol, pay not. If there ever does aught for naught, all us do us for this'n. All us do it for this'n. So, I mean, I looked up, like, the meaning of that one, and I was like, it's not very flattering. But anyway, yeah, we, so I packed up the kids and I was like, all right, we're going to ride to Ripley from where we live. And so we found the Nidderdale Greenway. From where we are, we had to get there first. And then we rode probably like a couple miles up the road, or up the Greenway. And I was like, you know, I think maybe today, being our first day, this is probably far enough. And the kids are like, oh, we can go further. So I was just like, nah, not today. So we turned around. On Tuesday, right, this is Monday, on Tuesday, we rode to that point. I was like, all right, how you feeling? Good. Okay, good. And then we rode like an extra mile. And we were probably... I mean, it was a good deal further, but then I looked at our map and it was like we're basically a third the way done with the whole round trip. And you guys are saying you want to go on, but like again, it's kind of sketchy because if we end up getting stuck there, right, then we're gonna have to take the bus back, and I don't know how the bus works. Um, especially with 3 bikes. So I was like, I don't know, maybe we'll go a little bit further. So we got to like a cow pasture where they had a pad that went from a gate across the greenway to another gate. And I said, okay, that sounds probably good enough. We'll stop here, we'll turn around, we'll go back home. And we did that. And like I said, that was like a third of the whole trip. And then on Wednesday, we went to that point, and the kids just kept riding. I'm like, all right, well, I guess we're going. So we ended up making it all the way to Ripley. And they were excited. We were just riding around the town and stuff like that until all the places opened, because it was still pretty early in the morning. We ended up sitting down at the Castle Ripley Tea House, had lunch there, and then they had an ice cream bar, and I was like, okay, well, not bar, but they had an ice cream shop as part of their, like, I don't know, it's weird. The tea room itself has like a kitchen, but they also have a cafe. I'm like, you know, how do you want to do that? So we walked in and looked around at their ice cream, and we're like, yeah, but Ripley's ice cream is like right over there, and it's allegedly world class, and so we're gonna wait. So we waited until Ripley's world famous ice cream opened. Had some there. Everybody was feeling good. We finally rode home all the way, and like our youngest did not complain until we were within a half mile of the house, and I was like, awesome. Good enough. Not gonna care. We're just gonna push through. It'll be fine. So we made it home, and he was feeling super proud of himself. Daughter was just like, it was a bike ride. Like, this is a random Wednesday. And then we got rained out the rest of the week. So Thursday, Friday, we were planning on going down, but we didn't. And then at some point they were like, well, why don't we just, or I was like, why don't we ride to Ripley? And they're like, but Mommy hasn't done any of that. She won't make it. And I'm like, okay. She hasn't done any of the training. That doesn't mean she's not good at riding a bike. Wouldn't say that to her face. Hey, Pin. How's it going? Good to see you. Yep, decided to break out Fourier series and boundary value transforms by Brown and Churchill. James Brown. Not the same one, of course. Tonight is hashtag not sponsored by Treason West Coast IPA. I like the can art on this one. It is bordering on sort of Matrixy. You got these like 3 guys over in the corner dressed like agents. So I don't know what exactly is going on there, but meeting with the deans. Nice, nice. Hope everything is going well at work. This West Coast IPA is also ever so slightly juicy, which was not something I was expecting. So I decided to break out some pineapple rings. That's kind of perfect. I wasn't expecting that. Okay. Don't eat the pineapple, then immediately drink the beer. It's okay. Well, certainly not spelled like that. Oh man, that was that was the terrible electric car that they made in Top Gear. Jiff. Alright, UV. So here this is going to be x times sine of kx over k minus integral of, this one is doable, v du. So we need the sine kx over k, we could put that on the outside if I wanted to, times dx. That's just equal to 2 over pi from 0 to pi. Right, sine of kx from 0 to pi is always going to be 0, so because k is an integer. Right, so then this is going to be a minus 2 over pi. Integral of sine is going to be a negative cosine, so that's plus. Cosine of kx, oops, over k squared. Evaluate from 0 to pi. Nope. 2 over k squared pi times cosine of k pi minus cosine of 0. Okay, so this is going to split amongst right. So it's either going to be even or cosine of k pi is going to be either 1 or negative 1 depending on whether k is even or odd. Cosine of 0 is just going to be 1, so that's always going to be minus 1. Right, so 2 over k squared pi times negative 1 to the, is it k or k plus 1? When k is 1, we get cosine of pi, which should be negative, so that's that. Yep, okay. 2 pi should be 2 pi should be 1, so negative 1 squared. Yep, minus 1. Okay. So that means that a sub k. So that means that f of x, which equals x, can be approximated by capital F of x, which equals a0 over 2, so pi over 2, plus sum, k goes from 1 to infinity, of a sub k to negative 1 to the k minus 2 over k squared pi times the cosine of kx. Kx? Kx. Yep. Right, cosine kx. Going from 1 to infinity. 1 to infinity. Cool. Okay. So this says that. Okay. So let's try it. Hey Anders, how's it going? Hope you're having fun, doing some awesome math. Let's take Desmos, and I'm going to take Excalibur to the other window. Ooh, nope. Okay, so we're going to do y equals x. Then we're going to do a crappy approximation of it, followed by better approximations of it. This will only work between 0 and pi. Okay, so we're going to center our window from 0 to 3.5-ish. And then just keep in mind that x equals pi. Right, we're going to keep this as kind of a dotted line like that. And thickness we'll do like 1. Right, make it small. Make it barely visible. Okay. And then, I wonder, can we do multiple? No. Okay. Worth a shot. X equals 0, which, of course, it's not really going to mean much in the long run here. It's barely visible at all on top of the axes, but whatever, it's fine. And then we're going to... We're doing alright. Attempting to do some Fourier series. Pi over 2. Alright, plus. So now we take our... let me define. Haha. F of capital F. That'll be fine. Capital F of x is equal to n. What do I want? Term of n. This is gonna hate me. Is equal to, that's gonna be 2 times the quantity -1 to the n okay, -1. We're not going to graph this one particularly. We just want values from it. And then divide by n squared times pi times the cosine of n x. Crap. Can we do n comma x? Looks like it. Okay. Oh man. This is gonna hate me so much. Oh no, we don't have to. We can just do this as separate thing. Right. So t sub n is this, and then we can multiply it by whatever cosine we need. Right, so we do t of 1 multiply by the cosine of 1x. Alright, so if I'm honest, I don't hate it already, and that's only one term. So do you all see why this is good? Wow, okay. I have to say, that is rather impressive. Thank you, hydrate, yes. After that amount of coughing. Hang on. Alright, just so you can see I'm not cheating. Okay, so plus. Now we do t of 2 times the cosine of 2x. Okay, so when I do this, it'll pop up here. This should be an even better representation than the one we just had. Not sure that I actually see much of a difference. So let's go like this. Ooh, I almost hit something that would probably have made a mess. Yeah, I'm not seeing any difference there. Huh. Well, that's no good. Oh! Never mind. Yeah. Even valued terms are going to be 0. Right? Because the numerator is going to be positive 1 minus 1. Okay, so here, right? So, Anders, we're doing Fourier series. And what this is we're trying to approximate our function all the way at the top. So y equals x. And we're going to go like that and just make it green. Okay. So all of our even valued terms are going to be 0 because we've got a negative 1 raised to an even power is 1 minus 1 as our next term. So never mind, that was never going to work. We'll just clear that and put this as 3x, and then we'll do t of 3. Now this one should be a better representation of y equals x, a straight line, than was our green, who's it's? The green cosine function. So we're going to thicken that up a bit, just so everybody can definitely see it. Okay, so when I put this in as t of 3, this should get us a better representation for the red line between 0 and pi than does our green one. Yep. Especially at the ends, but also it's closer in the middle. Right, so it is a closer representation of the red line than the green one was. Yep, and we only care about the area between 0 and pi, which again are going to be our dotted red lines that are vertical. Okay. So we're going to copy this line. Again, do as like this is our best version. And then we come up here and we say, okay, now add. This is going to be t of 5 times the cosine of 5x. So now we do t of 5, and again, we should get a better representation of our straight line, y equals x, than the green one was. And you could tell that this is a better representation, one, because the ends are extending further before they start deviating, and also, in the middle, you can actually see the green coming off of the purple. Right? Coming away from it. I guess not. That doesn't always necessarily mean it's better, but if we switch it, yeah, you can still see the purple one. But you see the red one here and the purple one that's kind of overlapping it for the most part, right? And then here our red is going straight like this, and it looks pretty close to the purple one. Again, green's deviating a little bit more in both directions. So this is our best representation so far. Okay, and then we're going to add t of 7 times the cosine of 7x. Again, same deal. This one should be better. Alright, it's extending further before it deviates, and also it is a straighter curve over this region than is the green one. Right? If you need to, you can always zoom in a little bit and try to see, like, okay, in this region, the purple one is closer to the red one than is the green one. Right? In this region here, we got the same thing. Purple is closer than the green one. In here, it's a little hard to tell. In some cases, the green one is a bit closer. But the amount that it's closer, again, overall, is going to be... we're going to be better off with the purple one as our approximation. And then when we start getting towards 0, it starts deviating significantly on both of them. So, okay, so then we go out here. We can do the same thing. We can do plus t of 9 cosine of 9x plus t of 11 times the cosine of 11x. Right, so every time we do this, we're going to keep getting better and better and better approximations because we're adding more terms, which are getting us closer to the actual value. So this is going to keep getting us closer and closer and closer to our straight line y equals x. Right, and then you zoom out and it looks absolutely ridiculous. Right, this is a sawtooth wave that we're getting. So it's a little bit like the function we're essentially trying to approximate here is the absolute value of x, but then it's a periodic absolute value between negative pi and positive pi. So that's really what we're trying to approximate, but we're just focusing on the region between 0 and pi. Anders, usually you can go least squares. So if you pick any number of data points along your line, and you say, okay, given these data points, which are either randomly selected or you can have them like evenly spaced or various other things, you could say, you know, which one of these has better... Silver, we are not, actually. We're doing a Fourier transform, or a Fourier series. And so we were looking at, like, how the Fourier series representation for y equals x is going to expand. And then using our coefficients that we found here, how that would work for all these things. Mm-hmm. Yeah, we had somebody come in earlier and say he was doing Fourier series in terms of sorry, that's presumptive. They were doing Fourier series in terms of electronics and arg. I don't remember now. But yeah, acoustics is another fun one. Oh, right, signals analysis. Yep. Analog electronics and signals analysis. Yep. I just rewound. Found their actual first message. Or... Man, that is what I did. Yeah, it does not hold for all values. Although, you would find that it holds for a preponderance of the values, right? That there is probably more than 50% total that would end up showing that. So one of the other ways that you could do it is do your series to some number of decimals. Yeah. And then find the difference between those two things. Right, find the area between the curves. So you could take the integral from 0 to pi of f at x minus capital F of x to some number of terms, right? dx. Do it like that. And say like, okay, compare the values of the area that you're going to get from this for each k value that you get. And so you're going to find that the eventual area for this, right, a sub k is going to be equal to this. A sub k plus 1 is always going to be less than or equal to a sub k. Well, I shouldn't say always, but for what we've seen, it does seem to converge. Recording different instruments and see how the fast Fourier transforms compared. Yeah. I was actually telling a story earlier. In our freshman year, I was a physics major, and like all of the physics majors who were in this class, I think there were 5 or 6 of us, got together and did a project. And we said, what we want to do is, and one guy had like the idea, and he said, absolutely, we're doing this. And his idea was that we took the fast Fourier transform of some sort of input noise, whatever it might be. His idea was that we started with whistling, and then it turns it into, using a fast Fourier transform, into ASCII. So it'll spit out whatever ASCII you want. So you could whistle a tune and it'll spit out like a message. In this case, it was not a useful message. I had it on for a while and just like do fast Fourier transform on like my music, and it would come up with, you know, absolute nonsense and stuff like that. And it was kind of funny just to let it run for a bit. He called it whiskey because you were whistling and it would output ASCII. So yeah, the area definitely. This is actually very much a Something you could do after Calc 2. And in fact, in our Calculus 2 class, we did stuff like this when we were looking at our series representations. And looking how the series are doing the integral test, right, on a series. This is almost identical to something like that. It's just in this case it was like we're messing all sorts of stuff up. This is fun. Right, if we really wanted to do that, right, this is the same as integral f of k dx plus area sub k is equal to the integral 0 to pi of lowercase f of x dx. This is the same thing as our integral representation for a series. K goes from 1 to n of our series a sub k plus some error sub k. Right, is equal to that integral. That's identical to the integral test that we were talking about in Calc 2. It's just in this case we're not doing that. We're saying that this is we want the area, which is the error, to be minimized. So like, what value are we going to get for these two particular functions, and therefore function representations, and therefore which one is better, right? Find the thing that has the least amount of area difference over the entire region. So you don't have to pick individual data points. Makes it way easier. Or, well, depends on if you have a good function that's nicely integrable, or if it's just like you're going to have to do numerical analysis. That's not fun. Hum. Oh, that's a good one. Oh, I see. I see what they're doing here. Yep, okay, never mind. Yes, numerical analysis is known as, yeah, close enough. So the other thing that goes on here is the Fourier sine series. They waited a while to bring this up because it uses the thing we just did, where the function is equal to f of x equals x. So in this one, they say what we're going to do is we're going to start with the start with a sine series rather than a cosine series, and have f of x be equal to x. Note what that's going to do. If we have a sine function that's attached to this, that's going to mean that what we're basically doing is looking at looking at a function that looks like this. So we end up with something that goes from 0 to pi is still going to have this like negative part to it. Sorry, this negative part too down here because it has a sine function that's attached. So it's going to have a negative value before 0. Right, and then at pi it's going to jolt back down to negative. Oh, that's fun. Okay. Right, the y values are going to be pi and negative pi for these because those are the what we're going to get for our x value. Almost completely forgot what that was going to be doing there. Right, so then this is going to be 2 pi. So this is going to... Now this function does not exist out here, but in theory, right, it should end up with the same values because of the periodicity of the function itself. Right, and that's going to do the same out here. So this is going to be there, this is going to jump down there, etc. So the part we care about is between 0 and pi, and then everything else following it and everything else prior to it is going to all follow suit. So to deal with this stuff, that means that we need to do integration by parts to knock this down. This is going to be our u, this is going to be our dv, just like we did before. So this is all going to be equal to 2 over pi times the quantity. uv, so x, v is going to be a negative cosine of kx over k. This stuff's either coming back or it's just because I have a, such a scaffolded understanding of how this all works from trigonometry and differential equations that I'm just okay with it. And I can't decide which. Porque no los dos. Alright, evaluated from 0 to pi. Take the integral 0 to pi of v du. So again, our negative cosine kx all over k times dx. It's going to be equal to all that up there. So that's going to be equal to 2 over pi times the quantity negative pi over k times negative 1 to the n. Alright, when k is 1, we want the cosine of 1 pi to be a negative 1. So yeah, we could just leave this as negative 1 to the k. We've got a negative 1 out front. We can either absorb it or not. I don't really care at this point. Minus 0 is going to be multiplied by x, which is 0, which is going to go away. So 0. Minus, this is going to end up being a plus. Cosine becomes a sine. Kx divided by k that was already there times another, so k squared, evaluated 0 to pi. 2 over pi times the quantity. This stuff over here is going to be the sine of pi, and the sine of 0 is both 0. So then this is going to be pi over k times negative 1 to the k plus 1. Or k minus 1. Or whatever you feel like, because that's all good. That pi is going to go with that pi. It's going to be equal to 2 over k times negative 1 to the k plus 1. Is b sub n. How are we doing? 2 over k times negative 1 to the k plus 1. Yep. Cool. So our x is going to be approximated by f of x equals sum 2 over k times negative 1 to the k plus 1. K goes from 1 to infinity times sine kx. Okay, so again, this is going to be summation k goes from 1 to infinity of b sub k times sine of kx overall. Probably should have led with that, but you know. Most of y'all are pretty okay with it. Alright, so f of x is equal to that thing. Okay. Alright, so let's do the same thing with Desmos then. Okay. Y equals x, we're going to go from 0 to pi, same as we did there. This time, this stuff is going away. We'll be okay with that. Sure hope. Actually, you know what? Let's include other stuff just so we can see that it's going to be the same on both sides. Right, we only care technically between 0 and pi, but it's still going to be useful here to get other stuff. So, twice the sum of, this is going to be, wait, hang on. T of n is going to be equal to, this was 2 times negative 1 to the n plus, parentheses, n plus 1 over n, I think, right? Yes. Okay. So we get rid of this. This is going to be y equals t of 1 times the sine of 1x. Okay, so this is terrible, right? But again, it's only one term, so naturally it's going to be pretty awful. Then we're going to add to that t of 2 times the sine of 2x. Okay, so in this case, our cosine is not going to, unlike our cosine, right? Series converges to 0 when x is an odd multiple of pi. So it seems like, because this is an odd periodic function, it is possible that the movement from one term to two terms might have actually made it worse overall. So like the total area might be worse. And in fact, like, yeah, that's a huge difference here, right? But this has to be 0 here. It's just always what's going to end up happening. So let's see what's going to happen if we increase t of 3 times the sine of 3x plus t of 4 times the sine of 4x plus t of 5 times the sine of 5x. Oops, 5x. Right? So as we see, as n increases, we're going to end up getting the that might do it. We didn't even need to do that. Awesome. Okay, so p is going to go from 1 to 30 as a possible movement here. So yeah, here we go. All right, so when p, that top value, is 1, then we end up getting this thing. Then we go to p2, p3, p is 4, p is 5, p is 6, 7, 8, 9, 10. So when we go to p equals 10, we start getting this like pretty decent approximation for a straight line, y equals x, between 0 and pi. Again, it's not great. You still got all this nonsense going on at the end, and this has to dive down in order to become periodic so that it still is able to get back down to this point when our periodic values at negative pi end up getting transferred over here to pi. So again, we keep increasing our value for p, and we get better and better and better approximations for the overall trend of this thing. So now if we like do both, right? This is a of n, and also this is b of n. And also a, oops, yeah, a of n is equal to what we did before. up with. All right, a sub n is equal to that one. That one right there. So let's do both things at the same time. So if a sub n is equal to twice parentheses negative 1, oops, double parentheses, to the n minus 1 over n squared pi. Okay, and then we have the not just b sub n, but also a sub n plus, right? A sub n times cosine of nx. Really? Add a slider for n? No. N is part of the... Oi. Order of operations did not fix that. That is awful. What are you doing? There we go. Well, that didn't do what I wanted. That shouldn't do anything, though. Hang on. Pi over 2 plus that. No, that didn't do it. Huh. Did I forget constants? 2 over pi of that. Ooh. Not quite. Oh, 2 over pi is already in there. Okay. Lol. Get wrecked. People trying to sell viewers, but we don't want them because we already have great viewers. We're trying to approximate we're trying to approximate y equals x by using both the sine and cosine Fourier series at the same time. It's kind of interesting that it doesn't get us anything good. If we just add them together. I mean, it's not going to be great necessarily, but right? Ooh. Okay. Okay. Huh. So I don't know what to do about that, but Trying to investigate a sequence of numbers. Is there any cool stuff that can be done? So, probably not. However, Ni Lunda Lunas Heel. Good evening and welcome. My name is Obi-Wan Pez, and this is Simplex Pachinko. I can take a look and see what I can do. But no, I don't. So I've not done any like real advanced mathematics in quite a while. This is kind of our first, thank you for the follow. This is kind of our first like, I hesitate to say major foray, but into any sort of advanced mathematics in years. So I specialized in differential equations, specifically in partial and nonlinear differential equations when I was doing my master's. I have taught ordinary differential equations probably 5 or 6 times, and for the most part I taught pre-calculus and calculus at the community college level for the last 15 years. So I haven't done a whole lot of math outside of pre-calculus and calculus level, which is kind of a shame, but if you're interested, sure, I can take a look. Let's see what happens. Binary third symbol placeholder. So yeah. I can take a look. For anybody who's curious, we do have a friend of ours who was here earlier and has graciously allowed us to use his Discord server. So if you are at all interested in joining our math community, this is one place to start. This is sort of the central repository for a lot of our community type information. And you can also get connected with all of these wonderful people, collectively known as the Math Chads. We have here Dawn, who does math, Zach at e to the 2i pi, Penn Center, en Stuckey, Obi, that's myself at n simplex pachinko, welcome, Danny Highway, and Dr. Gold at Actual Education. So this is our core group of 7, and that core group has started to grow significantly, so we probably need to change that pretty soon. Penn Center also has a section in Discord, which allows you to post stuff for, let's see, it's the Math Forum section. Excuse me, Maths Forum section. And also has a Maths chat, so if you are at all interested in going to either of those, we could take a look, see what happens. Right. So we were looking at our yep. So we're looking at our Fourier transform here. Again, we could check that and compare it to how either of the other two work separately. And I don't think in particular we're going to see huge, massive difference, especially at p equals 30, right? This is going to be at least reasonable in terms of its... If we do k and n, let this be k and this be k, this be k, this be k, and this be n, right? Does that just trade it up and we're good? Okay, fine. Could actually trade it out. There we go. Sum as k goes from 1 to n of a of k cosine kx. Okay, and then we go back. Say that this is going to be pi over 2 plus, nope, plus that. Right? And then we also do sum as k goes from 1 to n of b of k times the sine of kx. Cool. So yeah. So our blue, being the cosine by itself, is actually doing quite a lot of the heavy lifting here. And the purple, which is the combination of the two, is not, I mean, it's better, but it's not significantly better than the sine alone. Sorry, it is better than sine alone, somewhat significantly. Right. And that continues the trend down that way. So as we get close, our blue one, which is the cosine by itself, is actually significantly better until we get right to the end. Our sine is significantly worse by itself, but overall we could need a combination of the two in order to account for various other kinds of functions, so stuff that is not just y equals x. So whatever function we're trying to approximate, it kind of depends. Please can you stay even just for the night? I'm losing my way, but don't try to contain me, 'cause I'm still running wild. Running wild. Oh yeah. Running wild. Oh yeah. Can you stay even just for the night? I'm losing my way, but don't try to contain me, 'cause I'm still running wild. Running wild. Oh yeah. All right. Boo. Where are we? There we go. Scalatra. Let's bump that back one. There we go. Ugh, gross. Um, So I think going way back to the beginning of our discussion tonight, the product to sum deal that we were talking about way back here. Nope, even further. Where is it? There we go. Right, this product to sum deal. It was using two different things in order to make sure that our sine kx, sine jx didn't... Yeah, it's... Okay. So it's going to use, like, two separate things to make sure that we get our sine and our cosine k plus j and cosine k minus j at the same time. Yeah. Okay. So cosine of k minus j of x is equal to cosine kx cosine jx plus sine kx sine jx. Okay, and in that way, if we do cosine of parentheses k minus jx minus cosine k plus j times x. That's going to be equal to 2 sine kx sine jx. Ah, right. We had cosine up. No. Okay, so we actually want the two of them plus each other to get two of those. So we're gonna get a half. Okay, it's this thing, right? It's this thing. All right, integral cosine kx cosine jx dx is going to be equal to integral of, all right, now we do the whole parentheses thing, and then we go back to where we were over there. That was going to be 1/2 of cosine k plus j x plus cosine k minus j x dx from 0 to pi is equal to, this is 1/2, integral of a cosine is a sine of k plus j times x evaluated from 0 to pi. That's going to be 0 times the sine of k plus j, k minus j of x evaluated from 0 to pi is also going to be 0. But each of these things are going to then have a k plus j at the bottom, which doesn't change the fact that it's still 0, and a k minus j at the bottom. Right. So those are still all zeros, but nonetheless, just how it gets there is kind of important. All right, so that's the product to sum product to sum rule, which again we get from the two separate angle sum rules to get to that particular location. So that's this here. Cool. All right. Anybody have any other questions that they might be interested in for tonight? It's getting on toward 1:15. So I think we're probably gonna see who else is on. I know Don's been on for a bit, so we'll probably not go over to Don. Actual education, Dr. Gold got on about a half an hour ago. Astro Canuck, Potpourri, Europa Clipper launch delayed. Well, that's not really that surprising, I guess. Paleontologizing is talking about the dinosaur extinction. How do we know what actually killed the dinosaurs? Except birds. And was there a second asteroid? I heard about this. There was a potential second asteroid strike approximately 65 million years ago. Somewhere near, I want to say Scotland? Like off the coast of Scotland? Which may have, unless I just completely misunderstood the story. But anyway. Right. So we'll probably go over and see Dr. Gold. And we're going to head on over there. I hope you all have a good rest of your night, rest of your week. We're going to be coming back certainly on Friday for more for gamey type stuff, and possibly between now and then, either I'll drop something on YouTube, or I'll also stream it on Twitch for Slay the Princess. We want to probably finish up some of that, and or might do Satisfactory between now and then. So hope you all have a good rest of your week. My name is Obi-Wan Pez, and this is N Simplex Pachinko. Have a good night.